Good morning, one and all. Welcome to computer organization session. This is Dr. Diana here. We have seen, we've started with unit 1. We've seen the difference between computer organization and architecture, and we have seen what are the two different types of computer architecture. One is the von Neumann architecture, the other one is the uh, Harvard architecture. In the von Neumann architecture, we saw that the CPU has ALU and control unit, which interacts with a common random access memory, or the RAM. And this RAM holds both the instruction and the data together. And we have also seen a different type of architecture called as the Harvard architecture. In the Harvard architecture, we saw that the data and the instruction are held in two different memories. And we see the same control unit, ALU, and IO devices are present in the Harvard architecture also. And we started elaborating on the von Neumann architecture, and we saw that in this architecture, we think about a memory unit that holds instruction and operands or the data together in the same memory, and the instruction format consists of 16 bits, with the first 4 bits, or the most significant bits, 4 bits, represent the operation to be performed. It's also called as the opcode. And then following that is the 12 bits of address, which specify the data to be operated upon. And any data that is stored in the memory is of 16 bits. And this data can be read from the memory into the process register called as the accumulator. So this is what we have seen, and we also started looking into how the memory is organized internally. Now when we how a program is executed, this is how say for example, this is our memory, and in our memory, imagine we have the program written in the first we imagine the first few rows of the memory has got the program, and then we have seen how a data is stored and how addresses are being used, and then we concluded that all the data and instruction registers are of 16 bits length, and all address registers are 12-bit length. And we have seen the list of uh, registers available in the basic computer. So this is the list of registers available in our basic computer. In this we see, for addressing a memory of 4096 words and with 16 bits per word, we need few address registers, few registers that can hold instructions, few few registers that can hold data. Now, the first register we saw was the program counter, which is used for holding the address of the instruction that is to be executed next. The instruction register IR holds the instruction that is currently to be executed, and the data for that particular instruction is placed in the data register, and the address of that operand is placed in the address register. Using the address register, you read the data from memory, and that data is placed in the data register. And for operating on any data, the control unit or the ALU uses the accumulator as the scribbling pad. So it does an operation and stores the result back in the accumulator. And once this is done, it can also use another temporary register for storing any intermediate result, which is called as the temporary register. And if we note here, we can note all the the register which is used to store instruction, which is IR, and all the registers that are used to store data, which include data register, accumulator, and the temporary register, are 16-bit wide, and the address registers, both PC and AR, are 12 bits wide. Looking at this, we have seen the list of registers which is available in the basic computer. And using these registers, I need to perform some operations. So I need to design an arithmetic and logic unit and a control unit based on these registers. Now imagine the computer has got different types of instruction. Each instruction I should be able to identify what type of instruction it is, and the control unit should also be able to identify what operation it should perform. So the computer has got three basic types of instructions. The first one is the memory reference instruction. The second one is called as a register reference instruction, and the third one is called as the input output instruction. Now in the input output instruction, we are going to make use of the two 7-bit registers which are available in our architecture. The first thing we will see is a memory reference instruction. What is a memory reference instruction? Any instruction that helps you read something from memory or write something into memory is called as a memory reference instruction. So one of the data that you use, it can either be the input data of the instruction or the output data from doing an instruction. Say for example, a read data or a write data. All these are memory reference instructions. So every time I access the memory for reading or for writing, it is called as a memory reference instruction. This, as we already know, all instructions have 16 bits and the operation to be performed is given by the 3-bit opcode. Now I'll show you how it looks. This is the 16-bit instruction, and all computer instructions use these 3 bits, bits 12 to 14 as the opcode. Those 3 bits indicate the operation to be performed. 0 to 11 bits are used to hold the address, and the 15th bit is used for indicating the mode of the operation. Now, this 12 to 14 opcode bit set is going to be common for all the types of instruction. Now, imagine for a memory reference instruction, the rest of the 12, this is common for all computer instructions. The 15th bit is reserved bit, 14 to 12 is used for opcode, 0 to 11, which is 12 bits, is used for the address. Okay, this is common. And for a memory reference instruction, this 12, 0 to 11 is used for specifying an address. The address is the place where I can find the data for the operation. So that address is given in the instruction itself. 0 to 11 or the 12 bits constitute the address from which I have to bring the data. And 1 bit is used for specifying the addressing mode I. And I have mentioned here that it is 0 for direct address and 1 for indirect address. We will first look into the format and then we will see what is direct and indirect. Now this is how the address is going to be. So 0 to 11 bits specify the address for the operand or data. 12 to 14 bits specify the operation, which is called as the opcode. And the 15th bit is reserved, it is called as the bit I. It is reserved for indicating the addressing mode. It is 0 for direct addressing. It is 1 for indirect addressing. Okay. Now this I bit is going to tell how to use the address which is given in the instruction. So this 0 to 11 bits of this instruction has got some address. I need to use that address to find out or locate the data for my operation. The addressing mode means whatever is given in the instruction, I need to process it and find out the location of my address or of my data. So the process of identifying the location of my data from the information given in the instruction is called as addressing mode. So different modes are used to provide address in different forms. So from the different forms, I have to actually locate my data based on the addressing mode that is used. Imagine this is direct addressing mode. When I say direct, it means the first bit should be placed at 0, and then I have a 3-bit opcode. Here I have mentioned that it is add. So add is the opcode that I have, and I have an address which is 457. So when I look at this, what do I understand? This is an instruction. This instruction is available in memory at memory location 22. So 22 is the location in which this instruction is stored. The first bit, so this instruction has got 16 bits totally. The first bit is called as the addressing mode bit I, and its value is given as 0. And then you have 3 bits. Here a mnemonic of 3 bits is given. I can represent its binary value as 100, which is add. Here it is mentioned as add. Add is the operation that I need to perform. It is placed in the 12 to 14 bits, or it occupies 3 bits in the instruction. Following that, 0 to 11 bits are used to indicate the address of the operand. Operand means a data that is used for the operation. So the address of the operand given here is 457. This address is 12-bit length. If it is direct addressing mode, then the 457, which is given in the address of the instruction, gives directly the location of the operand. Or in other words, if I look at memory location addressed as 457, I'll find the operand there. Is that understandable? So the address of the operand is directly given in the address portion of the instruction. Such an addressing mode is called as direct addressing mode. It is indicated with the value 0 in the most significant bit of the instruction. So if I look here, this 0th location is called as the least significant bit, and this is called as the most significant bit, right? So a direct addressing mode is indicated with 0 in the most significant bit, and 457 directly gives me the address of the operand. When I say add, what happens is whatever is there in the accumulator, to that value the operand value is added and the result is stored back in the accumulator. Do you understand this diagram? So in direct mode, my instruction is placed somewhere in memory, and whatever is given as part of instruction and the address field gives the location of my operand. If I go to that address, I'll directly get my operand value, and it can be used for any operation that is given here, given in the instruction. Now look at indirect addressing mode. This is an example of indirect addressing mode. In indirect addressing mode, you can note that the MSB, or the most significant bit, or the addressing mode bit I, is marked as 1. So the value 1 is given for the most significant bit. And following 3 bits are used to indicate the opcode, which is given as add. And then following that, the 12 bits show the some address value. Okay, 300 is the address value given. This entire instruction is placed in the memory location 35. In indirect address, it means this 300 is not the place where I am going to find my operand. That's why I call it as indirect. So what will I find at the memory location 300? So if I go to memory location 300, I find another value, another 12-bit value or a 16-bit value. This 1350 is an address. Clear? So this is the address in which I will find the operand. Okay. Now here I have used a 12-bit value 300 in the instruction, and at that location I am not able to find my operand. At that location I find another address value, and in that address value I can see the operand. So I have not directly given the location of my operand in the instruction, but I have given an address where I can find the address of the operand. Clear? So one time I have to go and look in the memory for the location value, then at that particular location I can find the operand. So there are two memory references happening here. One is for finding the address of the operand. The second is for finding the operand itself. So we are referencing the memory twice in indirect addressing mode, and it is indicated by value 1 in the MSB of the instruction. Now when this happens, this operand value can be added to the content of the accumulator and the result is stored back in the accumulator. Do you find the difference between direct and indirect addressing mode? In direct addressing mode, the address is directly given in the instruction, and whatever is given in the instruction, if I go there, I'll be able to find the operand there. In indirect addressing, whatever is given in the instruction is the location of address of the operand. So 300 is the location of the address 1350, which is where I find the operand. So this is the difference between direct and indirect addressing mode. So this is the basic instruction format of a memory reference instruction. It has got the MSB or the addressing bit mode bit I. It can either be 0 or 1. Its value is 0 for direct addressing mode, and its value is 1 for indirect addressing mode. And then you have 3 bits 14 to 12, which represent the operation to be performed on the data, and it is called the opcode, and bits 0 to 11 indicate the address of that particular instruction. Now the second type of instruction is called as a register reference instruction. A register reference instruction is when I am transferring one data from the accumulator to a different register, or from a different register to the accumulator, or I am performing an arithmetic or a logic operation between the accumulator and another register. We have two other registers other than the accumulator. What are those? The data register and the temporary register. So I can hold some values at the data register or temporary register, and I can try to do some arithmetic operations with those registers. Such an operation is called as a register reference operation. For every register reference operation, the opcode is 111. For all register reference operations, the opcode given is 111, and we have a 0 on the MSB or the 15th bit. So the first 4 bits are going to be 0111 for all register reference instructions. Then how do I understand what operation to be performed? So when I am talking about registers, I am not going to access memory. So I am not going to make use of any address for accessing the memory. So in that case, the rest of the 12 bits 0 to 11 are going to be vacant. I am not going to use them for anything else. So those values, those bits are used to specify the operation to be performed. So a register reference instruction specifies an operation on or a test of the accumulator register or any other data register. So an operand from memory is not needed. Therefore, the 12 bits that are used to specify the operation. So whatever 12 bits we have from 0 to 11 are used to mention the operation code. So this is going to be our register reference instruction. The first, the MSB is 0 always. Following the opcode bits are set to 111. The rest of the 12 bits are used to indicate the register operation to be performed. Then we have the last type of instruction is the input-output instruction. In an input-output instruction, the opcode is given as 111 and the leftmost bit or the MSB or the addressing mode bit is always set to 1. So the first 4 bits are going to be 1111. And just like register reference instruction, I am not going to use the rest of the 12 bits to indicate any address in the memory. So those 12 bits can be used to specify the operation to be performed. So this is how my instruction is going to be. The 15th bit or the MSB is going to have 1. The bits 12 to 14, which is the opcode, are also going to have 1. So the first 4 bits are 1111, and the rest of the 12 bits 0 to 11 indicate what is the type of operation I have to performed. So these 12 bits are used to indicate the operation to be performed. So we have seen three different types of instructions. First is the memory reference instruction, the register reference instruction, and the input output instruction. These are the three types of instructions that we have seen today. In memory reference instruction, we have the first bit which is indicated as bit I, or the addressing mode bit, followed by 3 bits for opcode and 12 bits for addressing. And in register reference instruction, we have the first 4 bits set to 0111 and followed by 12 bits for specifying the operation code. And in the input output instruction, we see the first 4 bits are set to 1111 and the rest of the 12 bits indicate the input output operation to be performed. And we have also seen that this bit I indicates the addressing mode for the instruction. Addressing mode is a methodology of indicating how to locate a particular data from the information given in the instruction. There are two different addressing modes we have seen today. For direct addressing mode, the value of I is set to 0, and for indirect addressing mode, the value of I is set to 1. So this shows the difference between direct and indirect addressing. So when we use direct addressing, the location of the operand or the data is directly specified in the 12 bits of the instruction, just like shown here. So, and the first bit is set to 0. The MSB is 0, followed by the operation code, followed by 12 bits which indicate the location of the operand or the data. And in indirect addressing mode, the MSB is set to 1 and followed by 3 bits of opcode, followed by 12 bits of address. This 12 bits indicate the address at which I can find the location of the operand. So at 300, I find another value which specifies the location of the operand. So instead of directly telling the location of the operand, I am giving another place where I can find the operand. That is called as the indirect addressing mode. So we have, when we look into our syllabus, this is what we have seen till now. We have completed the block diagram of the basic computer, the definition of computer organization, computer design and architecture we have seen. We have also seen computer registers, what are the different instruction codes. An instruction code is something like a 16-bit value with 4 bits for opcode and 12 bits for address. That's called as an instruction code. Then we have seen computer registers. What are the different type of registers we have seen? Data register, accumulator, a temporary register and instruction register, all are 16-bit registers. And we have seen PC and PC program counter, and AR is the address register. Both are address registers that are 12-bit long, and two other registers, input and output registers, which are 8-bit long. Then we have also seen what are the three different types of instructions. The three different types of instructions are memory reference instruction, register reference instruction, and input output instruction. So with this I will stop for today's session. The next session we will look into timing and control and how an instruction cycle works. An instruction cycle is the most important question in this unit. We will look into it in the next session. We will see how a particular instruction is read from memory and how it is executed. We will also see how to design a circuit that can execute that particular instruction. So that is for our next session. For this session, I will close here. I wish I can see you all in person very soon. Stay home, stay safe, take care. Thank you one and all.